Right, thank you, Maria. Yes, I want to give the last of these 4 talks, and here I want to focus on energy minimization problems. So this talk, I've sort of, there's a lot I want to say about energy, more than I can in 45 minutes. So what I've done is I want to ask and answer 3 very concrete questions on this topic. And so in case during one of these answers of these questions you get lost or don't care, the next question you can catch along again. So yeah, we will basically here we will see everything I think that we did in the last 3 lectures. We will see it again in some form. So the first question I want to ask is also the question that was asked yesterday after the lecture. So how can we use the Laat hierarchy for binary polynomial optimization problems to, well, for instance, derive a hierarchy for energy minimization, right? So I want to show you how that can be done. So we've seen one example where we used this to derive a hierarchy for the independent set problem. And yeah, so here's a second example. So first, a little bit about the energy minimization problem. So sort of the main space we care about here is the sphere, and we want to, for instance, to minimize this this double sum. So oh, by the way, this should be I strictly less than j. Not I don't want to sum of all I and j. So this should be I strictly less than j. So you want to just sum over all the pairs, right? And then we minimize over all sets of exactly capital N distinct points. And well, if you do this for n is equal to 3, this is the Thomson problem. But of course, you can consider all kinds of variations. You can look at different pair potentials. So for instance, you can consider Riesz energy, where here you would put a to the power s for the Riesz s energy. Or of course, you can consider different spaces where you want to optimize particles. Yeah, so now I want to derive a hierarchy for this problem. So the first step, if you want to use this Laat techniques, is to sort of look at a different problem where the container, so let's call this the container where the particles live, is a finite set. So instead of considering the sphere, which is an infinite set, we consider energy minimization on this finite set. So from 1 through lowercase n. So how does that look? So here we take a symmetric matrix W, n by n, which plays the role of the pair potential. So if you think about it, so probably in applications, it should be entry-wise non-negative and plus infinity on the diagonal and symmetric. And then we want to find the minimum again of this. Okay, this should again be a sum over I strictly less than j, sorry about that. And now the particles, P1 through P capital N, there are n distinct points in this container, which is now the set 1 through lowercase n. Okay, so, and this we can write as a binary polynomial optimization problem. So how can we do that? So we take a quadratic objective function, or of course the sum should be I strictly less than j. Now x is a binary vector. Of course, if you want to write this really as a polynomial optimization problem, you would use quadratic polynomials to force x to be binary. But yeah, we're going to work in this framework that we saw for 0-1 polynomial optimization. So then we don't really want to use polynomials anymore to encode that. We just say x is binary, and then we want to use polynomials for the remaining constraints. And then also in our framework, we are always using inequality constraints. That's the way we discussed it. So we just get quadratic modules, otherwise you also get, you can also work with equality constraints and ideals and everything, but that's just complicating things. So we think of this equality constraints really as 2 inequality constraints. Okay, so let me recall the moment hierarchy for binary polynomial optimization. So here's a general binary polynomial optimization problem. So we minimize some polynomial x is binary and x lies in a semi-algebraic set. And then we get the following general moment hierarchy. So the objective, so we did I write that? So here we optimize over vectors y indexed by subsets of 1 through n. And this is, by the way, the exact same n as in our container of size at most 2t. We have this objective that corresponds to p of x, but now we use the moments here, the pseudo moments. We have the normalization constraints, and we have these constraints on the localizing matrices. So just to explain this notation again, so p of x, p sub s is then the coefficient of that monomial. And we assume that here there are no variables occurring with a power higher than 1, right? We can always make that assumption if you know we're working with a binary optimization problem. Again, just to repeat, so these are the localizing matrices. This looks a little bit complicated, but the thing you should focus on, I have this localizing matrix here. So if I take the entry on the jth row and the j prime column, it's this sum. So it's a sum involving, you can see this as a sum where the coefficients depend on the polynomial qs, and then we sum y subscript j union j prime union s. So that's the only thing you need to consider here. So so now we have a polynomial optimization problem for energy minimization on this finite container where the particles live. And I know, of course, small n is you should think of that small n is a much bigger number than capital N, right? These are the slots where the particles can be, and capital N is the number of particles that we put in these slots. So yeah, here's again the formulation as a polynomial optimization problem. So xi here indicates whether or not there is a particle in the ith position, right? So that's why we want the sum of the xi to be equal to the number of particles. Yeah, think of the diagonal of w being plus infinity if you don't want many particles on the same spot, but this is all not important. This is just you would just have to adapt the notation a little bit if you do that or not. Okay, so here we have a quadratic objective. So that means that the objective in the hierarchy is going to sum over we're going to sum here the vector y over subscripts of cardinality 2. And then we have the normalization condition and the localizing constraints. And here the set q is just the two polynomials there, q and minus q, where q is this constraint setting the number of particles equal to capital N. And now we can reduce it. So if you think about how was this localizing matrix defined, so if you plug in a minus sign in front of this q, that just becomes a minus sign in front of the matrix. So maybe I should show that. Right, if you think here, if you put a minus sign in front of q, here we get minus signs. So we just get minus this matrix. And that, so if a matrix is positive semidefinite and negative definite, then it must just be exactly equal to 0. So we get these constraints. Okay, so again here the definition of localizing matrices. So if you think about what we did for the independent set problem, there we had the issue that from the polynomial formulation of the problem, we got a lot of localizing matrices. And that's not clear how can you go from that to a hierarchy for an infinite problem. But then we used this result by Monique Laurent, that instead of all these localizing matrices, you can actually just say y has to be supported on the independent sets. And that's equivalent to all of these localizing matrices. So here we want to do something similar. So everything here is fine, except these localizing matrices, even though there are only two, it's still very complicated. So why is it very complicated? So let me show that. So here we have, again, the definition of the localizing matrices. So, and then this constraint, setting this matrix to 0 for this polynomial, this reduces to this very large set of constraints. So n times ys is the sum over I of ys union with I. So how can you see that? So this is the polynomial q. So if you think here, what happens here, you get the empty set here for s, and then you get an n as coefficient. So, and then for j, you can plug in any j and j prime. So that's going to be this n times ys. And then you get a sum over all singletons here. And that's this sum over the singletons. So, but these are a lot of constraints. And it's not necessarily that an infinite amount of constraints is problematic if you go to an infinite setting. But these ones will become a bit weird if you go. So what do we want to do here? We optimize over vectors y. So if you go to an infinite space, sort of the natural thing that you would want is you want to optimize over Borel measures on that space. But these constraints, then, they wouldn't say anything about this Borel, sort of the, how do I say that? So they wouldn't say anything on what this Borel measure is doing on open sets. So all these constraints, so these are just constraints of the Borel measure on sets of that are not of full dimension, right? Yeah, that is going to be just a bit weird, and that's going to really complicate going to a deal that you can actually do computations with. So we want to get rid of these constraints. And that can be done, well, the following lemma suggests how you should do that. Let's say it like that. So this lemma says that instead of all of these constraints, you can just, well, these, I should say, should be precise, what I want to say. So instead of these, so these constraints imply these 2t plus 1 very natural constraints. These constraints look very natural if you think of what a feasible solutions y are that you can construct from a particle configuration. And then we can just plug those constraints into the hierarchy and hope for the best, basically. So because I've never been able to prove the reverse of this lemma. So we don't, strictly speaking, we don't know that this hierarchy is as good as the previous hierarchy that we wrote with localizing matrices. But yeah, so this potentially makes the hierarchy weaker, but we can still prove finite convergence to the optimal energy in at most capital N steps, where this is capital N is the number of particles. And here is something very similar happens to what happened for the independence number. So if you go from a finite graph to an infinite graph, you could worry that you don't get finite convergence anymore because this convergence, well, if the number of steps in the hierarchy you need depends on the number of vertices, then you could be in trouble, right? Because you go to infinitely many vertices. So maybe you would only get asymptotic convergence or no convergence at all. But then for the independence number, it turns out that the level at which the hierarchy stabilizes is actually the independence number. And the independence number stays finite for the kind of problems you care about. And that's why for the independence number, you still got finite convergence. So here something very similar happens. So this hierarchy, this is still for the finite problem. It converges in n steps. But if we generalize again back from this finite set to this infinite set, and we go from vectors y to measures lambda, then this proof still works. So you still get convergence in n steps. So even though, strictly speaking, the hierarchy might be weaker, at least all levels except for the last one, yeah, it doesn't seem to be a big problem because you still get convergence. And I really don't know if it's weaker. I would guess it's actually not weaker, but I haven't been able to prove it. Okay, so and how do you go from this hierarchy to a hierarchy for infinite sets? It's exactly the same as what we did yesterday for packing. So I won't show it now, but you're going to replace this y by a measure lambda on the unit sphere or on the set of independents, yeah, or defined on the subsets of the unit sphere up to some cardinality. And then, yeah, everything, you just have this one localizing matrix left in the moment matrix. And so that all works the same as what we did yesterday. So I don't want to go into that now. Are there any questions so far? But so this is the first question that I wanted to do. Okay, so and of course you could imagine that there are many other problems where you can use a similar strategy as here.
So I think there is a question on the chat.
Oh, I don't know if I can see it.
Fabrizio wrote, you still use the notation I, but without the interpretation of independent sets?
Oh, that's a really good point. I probably should not do that. Where do I do that? I do that here. Yeah, so here think of the graph that has no edges at all. Yeah, this is just an artifact of the copy this lemma from the paper. Um, in the paper, I still use it. So actually, this sort of it's a little bit technical. So you want to really prove strong duality. Proving strong duality is always a sort of a very tricky thing, and you need to be very precise there. And there, I wanted sets to be compact. And then it's sort of useful. So if you do energy minimization, you have a pair potential that shoots to infinity as the distance goes to 0. You know that configurations where two particles are very close, they're incredibly bad. Right? So you can, a priori, you can already exclude those configurations. And that's what I did using this graph. It's just theoretical. In the computations, you don't see that actually. But it's not important. So instead of doing this, working with this, you could use work with multisets and then allow several particles at the same spot, but then the notation gets really messy, so I didn't want to do that. But yeah, that's a really good question. So this here actually you should just think of it as the set of all subsets up to cardinality 2t. Yeah, so thanks for that. That's a really, really good point. Any more questions?
No, Fabrizio is just saying, okay, thank you.
Ah, that's okay. Yeah. So yeah, let me continue with the second question. So no, so what I showed yesterday, if we, for instance, look at the Delsart bound, but then formulate it more like the low-frequency theta number for an infinite graph, and you optimize over kernels. And also in these hierarchies, both for packing and for energy, you want to set up the hierarchy, then dualize, and there you're going to optimize over positive definite kernels. So the question is, how can we actually do that? How can we optimize over those objects? And I want to go into that here, but sort of on a, yeah, I want to sort of explain how that works and why semidefinite programming is going to pop up here. So in the hierarchies for packing and energy, we need to optimize over positive definite kernels for some space X. So let's make that precise later. So just to repeat, a continuous kernel is said to be positive definite if these double sums are non-negative for all finite C in our space X and for all coefficient vectors. Now we may assume that K is invariant under the symmetry group of the optimization problem, right? So this is, as explained yesterday for the Delsart bound, this is a very common thing in optimization. If you see that your constraints and your objective, there's symmetric under some group action, then you, by averaging, you may assume that the things you're optimizing over are also symmetric under the same group action. So, and in all these optimization problems, for instance, if you look at problems on the sphere, everything is going to be, and yeah, everything is going to be symmetric under the orthogonal group. So yesterday we saw Schoenberg's theorem. So if you take a kernel, so if you take a continuous function from this product to R, which is ON invariant and which is positive definite, then Schoenberg says that this is actually the following series. So if non-negative coefficient Ck, and we have these Gegenbauer polynomials, so these ultra-spherical polynomials, where n indicates the dimension of the space, and k is the degree of the polynomial. But what if we wouldn't know about Schoenberg's theorem? So how can we derive this? Because if we can derive this, then we maybe also be able to derive such an expression for the more general setting where we have a general space X here and some group acting on X. So let's see how this works. So yeah, we have the action of the orthogonal group on the unit sphere. And this defines an action on the space of continuous functions on the unit sphere. So it looks like this. So if we, so A here is an element from the orthogonal group. So A acts on the function f. So AF is a new function. If we evaluate that at a point x, then we get, then we need to compute f of the inverse of A applied to x. So you might wonder, why is this inverse here? Isn't that just making things overly complicated? But the reason is, so this is going to be a linear action, and also you want it to be a homomorphism from the group to the space of operators on your space of functions. So basically, if you change this thing, you want things to work out nicely. Yeah, and then you might think, okay, this situation maybe is too symmetric for anything interesting to happen, but that's not true. I think very interesting things happen if you consider this action on functions. So first the definition, so a subset or subspace of this space of functions is said to be invariant is if AF is in the space for all elements from the group A and for all elements in the elements F in the subspace. And then a second definition, so an invariant subspace is said to be irreducible if you cannot decompose it as a direct sum of non-trivial invariant subspaces. So you can imagine you have these subspaces, your group action is sending functions from somewhere in the subspace to somewhere else in the subspace. And if it would not be irreducible, then you could write the subspace as a direct sum of subspace where the group is really acting. So if the group acts on an element in one of these components, it sends it to another element in one of those components, in the same component, right? But if it's irreducible, that's impossible to do. You cannot really, you cannot take them apart further. So these are the atoms of the yeah, it is of the representation. I didn't use that word here, but it's what's behind this. So what we can do now, we can decompose this set of functions as a direct sum of irreducible subspaces. We call them HK. And so for the sphere and with the orthogonal group, these are going to be the spaces of spherical harmonics. So HK is going to be the span of a bunch of functions on the unit sphere. And spherical harmonics are really the generalization of just the cosine and the sine to higher dimensions. Yeah, and then what I want to work towards is Buckner's theorem. So in this case, Buckner's theorem says that if K is a positive definite ON invariant kernel on the unit sphere, then you can always write it like this. So this is a sum. So I messed up here. So these two, okay, all pi's in this expression should be K. So this is K, this is K, and this is K. And these two are also K. So all the pi's here should be K. So we sum over K, CK, and then we sum over J from 1 to the dimension of this, this space of circular harmonics, and we just multiply them. And here I'm assuming we took real valued circular harmonics. It's not important, otherwise you write it slightly different. Yeah, so how do we get Schoenberg's theorem from this? So that's the addition formula. So the addition formula says that if you sum these spherical harmonics in this way, we get the kth Gegenbauer polynomial of the evaluated at the dot product. And then if you plug this in, the addition formula, into this Buckner's theorem, we get exactly back Schoenberg's theorem, right? So let me just show you Schoenberg's theorem again. Right, there we said it's a sum over k non-negative coefficients of these Gegenbauer polynomials. And that's exactly what we get here. Okay, so but now this is not the full generality of Buckner's theorem, because there's something very special happens here that in many other cases does not happen. And that is this So I say here we decompose this space of functions as a direct sum of irreducible subspaces. And as you can, it's not difficult to see that all these spaces of spherical harmonics, they all have different dimensions. And that means in particular that they're not equivalent. So I'll say a little bit more about what I mean by equivalent. But all these irreducible subspaces, they are inequivalent to each other. And in that case, we have this form of Buckner's theorem, but in general, that doesn't happen. So let me explain what happens in general. So in general, we can have irreducible subspaces that are equivalent. So an equivalent here means that the spaces are, well, first isometric as vector spaces, so they have the same dimension, but also that the group acts in the exact same way in both spaces. So there's a way of making that precise, but that's not so important right now. Basically, you want to have an isomorphism between the two spaces that is equivariant for the group action. But you can just think of, you have two spaces and the group acts, so you can build a basis in each of the spaces, and you pick your favorite basis element and apply a group action to it. It's going to be some linear combination of the other basis elements. And then there's a way of defining these bases on those subspaces that this linear combination is going to look exactly the same for any group element. So it's really they are indistinguishable from a point of representation theory. And then if you can have equivalent subspaces, you need to write the decomposition like this. So here we have a sum over pi. So pi is here just, in general, all the irreducible representations of our group without repetition. And then this n pi denotes how often the representation pi, appears, so how many equivalent copies appear in this space of functions. And then we use the notation h pi I, and we also want to consider a basis of that space. So we say h pi I is the span of the functions e pi ij, where j runs from 1 to n pi. And then the general form of Buckner's theorem looks like this. So we say that k of xy is the sum over all the irreducible representations without repetition. And then the c pi here is the coefficient, the pi coefficient, but this now is a positive semidefinite matrix. This is the trace inner product, and these matrices are called zonal matrices, and they're defined like this. So that looks quite similar to before. So if you take this matrix, the I, I prime entry is defined like this. And if you think again about Schoenberg's theorem, there n pi is equal to 1. You don't have equivalent copies, so this disappears. Here the I is just always 1, so it sort of disappears from the notation. And then here you get 1 by 1 matrices, which means that your coefficient matrices are also 1 by 1 positive semidefinite matrices, which are just non-negative scalars, right? So you're back in that setting. So, and I wanted to explain it up to here. I don't want to say more about it now. I want to go through up to here so that you see why positive semidefinite matrices also appear here, right? Of course, that's very natural because we considered positive definite kernels. But yeah, there's a lot more you can say about this, because now the question is computing these. If you really want to run computations with this, you need to have zpi explicitly in the computer, right? You need to explicitly write a file that you at some point put in your semidefinite programming solver, and to build that file, you really need to have the zonal matrix explicitly. And that is actually, there's a lot of interesting things there going on. So for instance, I'll talk a little bit about computing the second level of these hierarchies. And then you have to consider kernels on the space X, where X is the set of independent sets up to cardinality 2. So there's basically going to be a product of spheres. And then, yeah, you need to work out this decomposition for a product of spheres. And for that, you can, for instance, use the Clebsch-Gordon coefficients that physicists are very familiar with to do that explicitly. Yeah, now I want to continue with the third question, if there are no questions about this. Okay, so let's go to the, oh yeah, CPI is plus the semidefinite, I said it already. So let's go to the third question. So how do we deal with the inequality constraints? So yesterday we saw the Delsart bound, and there was this polynomial that needed to be non-positive or at most -1 or something on an interval. And that's why I didn't really want to call it a linear program, but more like a semi-infinite linear program, because yeah, you still somehow need to deal with all these inequalities. And this is something that happens also if you work out the dual of these hierarchies, you get a lot of these inequality constraints. So how can we deal with them? So let's go back to the first of the 4 talks I gave. So there we considered central squares. So we considered a polynomial optimization problem of this form. So we minimize P of x over x in the semi-algebraic set with a semi-algebraic set. So by the way, I always just say semi-algebraic set, which is true, but strictly speaking, this is a special type of semi-algebraic set, a basic closed semi-algebraic set, but let's not worry about that here. So this is an example of a semi-algebraic set. So we have all x, where q of x is non-negative for all q and q. And to work with sum of squares, we first needed to reformulate this. So we wrote this, instead of looking at this directly, we maximize over scalar c, such that p of x minus c is a non-negative polynomial on this semi-algebraic set. And then we could use sum of squares. Then we could say, instead of this, we say that p minus c must lie in some truncated quadratic module, right? And then it's a semi-definite programming hierarchy. But now actually we don't even have to do such a reformulation. So let me show what's going to happen. So here we have an example of the Delsart bound, right? So we have an objective, we have definition of this function in terms of Gegenbauer polynomials. We have this non-negative constants that we optimize over, non-negative coefficients that we optimize over. And we have this polynomial inequality constraint. So it's already here. So if you take this and just rewrite it to say 1 minus f is non-negative on this interval, then we can now use the truncated quadratic module here, right? So this interval is semi-algebraic. So we can write it, well, there's 2 ways of writing it, 2 obvious ways of writing it. So you could say it's a set of all x such that x minus cosine theta is larger than 1 and 1 minus x is larger than 0. So x minus cosine theta non-negative and 1 minus x non-negative. Or you can say that this product is non-negative, that's the same. And then you can, so we can use Puttiner's theorem, right? We can write this using a truncated quadratic module. But here actually, because this is the one-dimensional case, we can use a much older result. So instead of using Puttiner's theorem, we can use a result by Lucas. So we have this polynomial. If this polynomial is non-negative on this interval, that implies that P lies in this quadratic module if the degree is odd. So so we make a case distinction between even and odd degrees. That's just a bit nicer. So if the degree is odd, it lies in this quadratic module where we use these linear polynomials. And I did a copy-paste error. This should be the quadratic polynomial. So this should be x minus cosine theta times 1 minus x is non-negative. That's if the degree of p is even. And so the situation here in the one-dimensional case is quite a bit different from what we did in general, Puttiner's result, because for Puttiner we didn't have, well, there's an effective version where you get a degree bound, but this degree bound is absolutely terrible. But here in the one-dimensional case, we really get a degree bound. So we get an exact, so we really get a semidefinite program that exactly solves what we want to solve in this case. Yeah, but more generally, so and that's especially if you're going to work with this hierarchy beyond the first step, we can consider semidefinite programs where we have polynomials whose coefficients depend linearly on the entries in the matrix variables, and which need to be non-negative on the semi-algebraic set. So let me go back to Del Start to just explain what this means. So here we have a polynomial, 1 minus f of u. And if you write this out as a polynomial in u, the coefficients are linear functions of ck, right? So the coefficients are linear functions of the entries of the matrix variable. These are all, if you think of this as a semi-definite program, these are all 1 by 1 matrices. And then that polynomial needs to be non-negative. So in the general setting, you have polynomials whose coefficients depend linearly on the entries in the matrix variables, and which need to be non-negative on semi-algebraic sets. And then we can just use Putanov's theorem and model this using truncated quadratic modules. And that turns this into a semi-definite program. But of course, then we don't have a good degree bound, so we need to make these degrees bigger and bigger and hope for the best. But in practice, this works really well even for small degrees. Yeah, now this is an important point that I don't really say anything about that. So when we were talking about this harmonic analysis for the hierarchy, we used that the sphere is very symmetric. We have the orthogonal group, and that's going to help in optimizing over the kernels. So here there's actually another symmetry in these problems that's really important, and that's the particles are all the same. So we get a symmetric group action also, and that is going to appear in the polynomials that need to be non-negative. They are going to be invariant under the symmetric group. So you can see the paper by Gederman and Perillo to see how you can work with symmetric sets of squares constraints. So I'll put a reference later. So now so that were the 3 questions I want to do. So are there questions now about this? Otherwise I go to the last slides. Okay, so yeah, now I want to say a little bit about, so we in the first question we saw how we can derive a hierarchy for energy minimization. So I want to say a little bit about how we can actually do computations with this. And these are just basically going to be a summary of all the steps we saw. So the first step is that we set up a moment hierarchy for this problem by first considering energy minimization on this finite set 1 through n, and then applying the Lasserre moment hierarchy to that and see how it looks. And then sort of reformulating this into a shape that allows us to generalize this to an infinite set, right? That's the game we're playing there. And then if we have this hierarchy for the infinite set, for the infinite problem on the sphere. So these are relaxations, but to get rigorous bounds, we want to compute feasible solutions of the dual. So we consider the dual hierarchy, and this is going to be optimization over continuous positive definite kernels. And of course, we may now assume that these kernels are going to be invariant under the symmetry group of the problem, which is, well, going to be the orthogonal group if we consider problems on the sphere. Yeah, and then we realized that the first step in this hierarchy is Udin's bound, which is the energy minimization version of the Del-Start bound. So that's not interesting if you want to compute better bounds, so we consider the second step. Yeah, and then we use harmonic analysis to find an efficient parameterization of the space where these positive kernels live by semi-definite matrices. And so the important thing here is that you need to find some way to do this explicitly so that you can really put things into a computer. And then then we are left with a problem with a lot of positive semi-definite matrices, but also with polynomial inequality constraints. So we use symmetric central squares characterizations to deal with these polynomial inequality constraints. Yeah, and then we really have a semi-definite program, and you can write some code to really generate the solver input of this semi-definite program. And then we solve this, and so in practice we use STPA-QD or STPA-GMP, because machine precision turns out to be not enough for these kind of problems, or that's not really nice enough. So we want to use higher precision. These solvers, of course, are slower than machine precision solvers, but they're actually pretty good. We can get some very high precision results of this. So STPA-QD uses a quad double precision, and STPA-GMP uses any precision you want. So you can use, for instance, 5,000 bits per number if you want. You can do really ridiculous things. Yeah, so I want to mention one application where this computation worked out. So the Thomson problem for 5 particles on the 2-dimensional sphere, this was solved by Swartz in 2015, but he didn't use a certificate. So he really somehow find a very clever way of discretizing this infinite search space of where these 5 particles can live, and then really going through the whole search space. So that's a very nice result, but it's not with a certificate. So we would also like to reprove this result using a certificate. But Judith's bound and the 3-point bound by Cohn and Wu, they are not sharp here, so they cannot give us this certificate. They can give a bound on the energy, but they don't give a sharp bound, so they cannot prove that the configuration is optimal. So, and then the second step of this hierarchy turns out to be numerically sharp. And what do I mean by numerically sharp? So we get, well, at least, I used STPA-QD here. So we get at least 28 of the, so the optimal energy is some algebraic number, and we get at least 28 of the decimal digits of this algebraic number correct. Yeah, and then of course it would be nice to be able to, this is not yet, it is numerically sharp, right? It's not yet a proof that this is sharp. And together with Maria Dostert and Philippe Mestreau, we have a paper where we talk about rounding the floating point output of a semidefinite program to exact rational or exact numbers in a number field. And Philippe will talk about it tomorrow, I think. Yeah, so before I finish, quickly an advertisement. So this actually have a PhD position in Delft, and I have some projects in mind for this position also that have a lot of to do with the 4 talks I gave here. And the application deadline is 1st of October. So if you're interested or if you know someone